So now we've gone over changes in motion and we've looked at Newton's first law. It's time to move on to Newton's second and third laws, which are part 3 of chapter 4. I'll start by introducing Newton's second law. This law states that the acceleration of an object is directly proportional to the force acting on it and inversely proportional to its mass. Let's go back to the example of the car and the truck to figure out what this means. It seems fairly intuitive that as the force pushing on an object gets bigger, it will accelerate more, because forces cause acceleration. And as we've seen, it takes much less force for somebody to push an object of smaller mass than it does to push an object of bigger mass. That means that as the mass gets bigger, the acceleration will get smaller. So, they're inversely related. We can look at this mathematical model, A equals F over M. And we're going to simplify this a little bit to get to Newton's second law. We'll multiply the m over to the other side, get F equals ma, or force equals mass times acceleration. This will become a fundamental equation when we're studying situations with objects that have force being applied to them. On to Newton's third law. This law states, for every action, there is an equal and opposite reaction. Let's look at some situations. We have an object, block 1, that's acting on block 2. As much force as block 1 exerts on block 2 will exert an equal amount of force back on block 1. We can look at the example of the book on the table to explain this further. As much as the book pushes down with its weight on the table will exert an equal force in the opposite direction back on the book to keep it supported on the table. That's Newton's third law. So objects that exert equal and opposite forces on one another, such as blocks 1 and 2, or the book and the table above, are known as an action-reaction pair. And it's important to keep in mind that action-reaction pairs do not always have to be contact forces. Field forces, such as the force of gravity on the Earth, can also exist in pairs. Let's look at how that works a little more. We have a person on the Earth. The Earth is exerting a force of gravity that's accelerating the person to the Earth. According to this law, the person should be exerting an equal force on the Earth as the force that the Earth is exerting on the person. To understand how this works a little bit better, and why the Earth isn't accelerating towards the person at the rate of g, or 9.81 meters per second squared, we'll go back to Newton's second law. Force equals mass times acceleration. The forces may be equal for the person and the Earth. We'll call this the force of the person on the Earth and the force of the Earth on the person. But the Earth's mass is so much greater that the acceleration must be extremely small to keep this force equal. That's why we don't notice the Earth accelerating towards things as they fall to the ground. Let's do some practice with the second and third laws. Number 1. A 6 kilogram object undergoes an acceleration of 2 meters per second squared. What is the net force acting on the object? So let's set up the equation. Force equals mass times acceleration. We're solving for net force, so we'll leave that as F. We know that the mass is 6 kilograms. We also know that the acceleration is 2 meters per second squared. So force will be 6 times 2, or 12 newtons. That's the final answer. Now we want to know what acceleration is produced if the same force is applied to a 4 kilogram object. Let's take a look at that. Now we know the force. The force is 12 newtons. We also know the mass, 4 kilograms, but we're solving for acceleration. In order to do that, we'll have to divide both sides by 4. Now we get acceleration equals 3 meters per second squared. Number 2. A 10 kilogram bike starts from rest and rolls 10 meters down the road in 2 seconds. What net force, so we're solving for force, F, acts on the bike along the road? Let's start by solving for the bike's average velocity. We know that the bike travels 10 meters in 2 seconds, so its average velocity must be 5 meters per second. We'll call that V average. Now, once we know the average velocity, we can set up this equation. V average equals V initial plus V final over 2. We learned this in chapter 2. Now we know V average, that's 5. It started from rest, so V initial must be 0. V final is what we're solving for, divided by 2. Multiplying the 2 over to the other side, we can see that the final velocity is 10 meters per second. Now let's solve for acceleration. We see that the object accelerates from 0 meters per second to 10 meters per second in 2 seconds. That makes its change in velocity 10 meters per second. The change in time was 2 seconds, so acceleration is 5 meters per second squared. There's only one final step. We're solving for force, so let's set up the equation force equals mass times acceleration. We don't know the force yet, however we do know the mass, which is 10 kilograms, and we know the acceleration, 5 meters per second squared. Therefore, the force on the bike over this interval is 50 newtons. Practice number 3. What force is required to keep a 5,000 kilogram object moving at a constant velocity of 7,500 meters per second? So you might already have an idea as to what the answer is here, but let's set up the equation just to make sure. We're solving for force once again. M, mass, is 5,000 kilograms. Now we come to acceleration. We see that the object is moving at constant velocity, therefore the acceleration is 0. This means that there is no force acting on the object, or if there is a force, it's cancelled out by another. In other words, the net force on the object is 0. And a key indicator of that is constant velocity, because if an object is moving at constant velocity, we know that the net force on it is 0. Number 4. A person standing on a horizontal floor feels two forces, the downward pull of gravity and the upward supporting force of the floor. These two forces, A, have equal magnitude and form an action-reaction pair. B, have equal magnitude but do not form an action-reaction pair. C, have unequal magnitude and form an action-reaction pair. Or D, have unequal magnitude and do not form an action-reaction pair. So we'll start by thinking about the position of a person. This person is standing still on the floor. That means the person's at rest, so the net force on the person is 0. If the net force on the person is 0, then the upward and downward pulls must be equal. That means that right off the bat we can get rid of C and D, because we know that the forces have equal magnitude. Now let's look at A and B. We know that an action-reaction pair is a situation in which an object 1 exerts a force on object 2, and object 2 exerts a force back on object 1. We see that gravity is exerting a force on the person, and the floor is exerting a force on the person, but gravity is not exerting a force on the floor. Therefore, the forces do not form an action-reaction pair because they're not acting on one another. That leaves us with answer B. They have equal magnitudes but do not form an action-reaction pair.